Hello everyone. In this video, we are going to talk about the work kinetic energy theorem. Okay. So in last video, previous videos we introduced so how to calculate the work. So and then we were trying to relate the work to kinetic energy. In fact, there are many ways to prove work kinetic energy theorem, but we just use a simple one first. Okay, let's use what we learned in constant acceleration motion in chapter 2. Yeah, chapter 2. Okay, we use the constant acceleration motion and also assume the 1D constant acceleration motion to prove the kinetic energy theorem. Yeah, suppose we have a net force sigma F, the net force pulling the object from the initial position to the final position. Okay, and the displacement is called delta x. And initial velocity of object is vi, and after pulling the object over delta x distance, and its velocity become vf. Okay, so we can use this usual to prove the work kinetic energy theorem and make a definition of what's the so-called kinetic energy. Okay, so let's we start with there's a equation of motion, right? Yeah, that's three. There's an equation of motion for constant acceleration, and it is like looks at this. But I rarely use this equation. You know, I like the other two equation of motion. This equation of motion I rarely use, but use this equation we can prove the work kinetic energy theory very quickly. Okay, it's Vf squared equal to Vi squared plus 2 times acceleration and delta x. Okay, and so we replace the acceleration by Newton's second law. So Newton's second law says, Newton's second law, Newton's second law, what Newton's second law says is your net force equals to mass times acceleration. So let's right now all assume it's one dimension work. So let's get rid of the vector. Okay, let's make life easier. So we can replace A by the summation net force divided by mass. Okay, so what we get, Vf squared equal to Vi squared plus 2 summation F divided by M and times delta X. And if you remember the definition of work, so this is work, sigma F times delta X. Okay, because we assume it's right now we assume it's 1D work, 1D motion. So the summation, the net force, the direction of summation force, or sorry, the direction of net force is equal to the direction. Parallel to the direction of displacement vector. So this is W. Okay, work. Okay, work. Okay. So after you realize this, so what will you get? You will get Vf squared equal to initial velocity squared plus m and 2w work. So we will reach this one. So your work is equal to 1 over 2m Vf squared minus 1 over 2m times Vi squared. Okay, so your work is, you'll get the work expression. It's the work can be related to your velocity. Okay, and from this theorem we define a term so-called kinetic energy. We define a term called kinetic energy. Kinetic energy, in this course we use K to express the kinetic energy, is equal to 1 over 2 mv squared. Okay, this is called kinetic energy. Kinetic energy. So your work is equal to the final state kinetic energy minus initial state kinetic energy. Okay, that's the conclusion of the work kinetic energy theorem. Your work is equal to the kinetic energy difference between the final state and initial state. Okay. Yeah, they always care about the final state energy and final state kinetic energy and initial state kinetic energy. Anything happen between them, doesn't matter. We only care about the final state and initial state. Anything happen between them, yeah, go fuck themselves. We don't care. Yeah, that's this is so in physics there are lots of formula like this. You only care about the final state and initial state. Anything happen between them, we don't care. Go fuck themselves. Okay. This style it happens in maybe later potential energy, elastic potential energy, and gravitational potential energy. They only care about final state, initial state, and also the displacement. Like in the first, not first, the chapter 2, we introduce the displacement, right? Displacement also care about the initial position and final position. Difference between the final position and initial position. We don't care anything happen between them. Yeah, so that's the style in physics. So that's why I like physics. I only care about your final state and initial state. Anything has to happen between them, go fuck themselves. Okay, I don't want to know. I just care your final state, initial state. So that's a very philosophy. Okay, so this is very using the constant acceleration motion to prove the world kinetic energy theorem. And from this theory, we can also elaborate more. So, if you are doing positive work, like I said, the work can be positive or negative. Yeah, work can be positive and negative. If you do a positive work, that means work is greater than zero. If you do a negative work, that means your work is less than zero. So if work greater than zero, let's do the implication. Your final velocity is greater than your initial velocity. You are doing negative work, that implies your final velocity is smaller than your initial velocity. So by observing the velocity change, okay, you see by observing the velocity change, you can calculate the work. Okay, so work is related to your velocity. Work has a close relationship to velocity. So by observing the velocity, you can understand you are doing the positive work or negative work. Yeah, if you slow down, the motion slow down, then means some force doing the negative work. If the object speed is increasing, that means some force is doing the positive work. Okay, so that's the conclusion of work kinetic energy theory. Okay, let's go back to the slide. So, and like I said, there are plenty ways to prove this theorem. And in textbook, it use the integration to prove this theorem. So let's take a look at this and use some calculus trick. So if you can accept that, just accept that. But if you cannot understand, doesn't matter because we already use the constant acceleration motion to prove this theorem. So let's say, okay, it's work and use integration because this is most general way to calculate the work. Doing the integration with respect to x and doing the integration on net force and with respect to x, and use the Newton's second law, F equal to ma. And acceleration is the derivative of velocity with respect to time. And from here to here, he used a calculus trick. Yeah, that's just as I said. If you can accept that, okay, take this. But if you cannot understand, later you will understand because this must be taught in calculus. Yeah, it's just a matter of time. So from here to here, he make a trick. He use here we have a dv over dt and dx. So he make a trick. He intentionally make the dx divided by dt and multiply dt again. Okay, and you do this cancel out. So when you will left with m, and this will become v. You are left mv dv. Okay, it's called a changing variable. You will learn this in calculus. This skill is called changing variable. And initially, you are doing the integration with respect to x. So the initial, integration range is start from xi to xf. But once you change the variable from x to velocity, your integration range also has to be changed. So it changed from the initial velocity to final velocity. So we assume the mass is a constant. Yeah, in most of time, mass is constant, so factor the mass out, and you have v dv and vi, range vi, vf. So this is a power function integration. Like I said, power function integration is very easy. So I don't want to address more. Okay, prove yourself. Okay, v squared minus vi squared. So the conclusion is the same same as when we use the constant acceleration motion. Yes, it must be the same. Constant acceleration motion is a special case, and this proof is more general case. So it must be have the same conclusion, right? Okay, so that's the proof of the work kinetic energy theorem. And one last thing I want to address is the kinetic energy. Yeah, because the motion is in 3 dimension, in 2 dimension or 3 dimensions. So your kinetic energy can be decomposed in 3 contributions. X component, kinetic energy from X component, kinetic energy from the Y component, kinetic energy from the Z component. So what's this component? Yeah, actually, kinetic energy is scalar. Okay, kinetic energy is a scalar. That's true. But we can how to say that we can this is the total kinetic energy contribution. We can classify or separate the contribution from each direction to the kinetic energy. So, for example, if for the x component kinetic energy from component, that means 1/2, and so Vx squared, okay, is equal to the x component of velocity square. And ky is 1/2 m times y component velocity square, and kz is 1/2 mass times the z component velocity square. Okay, so the total kinetic energy can be separate into three dimension, 3 contribution from each dimension. Okay, for example, in previously we have shown example a rabbit 2D motion of the rabbit. And in that example, we finally get the velocity vector. Yeah, I remember it's when t equal to 15. That's the example in chapter 2, right? In chapter 2 lecture. So what's the answer? Let me see. No. Yeah. In that example, we finally get at a t at a time equal to 15 seconds, the velocity vector of the rabbit is minus 2.1 I and plus minus 2.5 J. Okay, if I assume the mass of the rabbit is what 2.5 kilogram. Okay, and what's the kinetic energy of this rabbit at this moment? Okay, it's simple because this is 2D motion. Okay, so we can decompose the total kinetic energy in from x component and y component. So the total kinetic energy is 1/2, 2.5, and minus 2.1 square plus 1/2. Mass is 2.5 and minus 2.5 square. So you add them totally. So what's the final value? It's 13.32. Okay, 13.32 joule. Okay, that's a simple example to just show you. Okay, total kinetic energy can be decomposed into the contribution from three directions. Okay, and this is useful because you remember in high school when you try to derive the ideal gas law. Ideal gas law. Remember that there's an equation for ideal gas law. Okay, and we use this concept to prove the ideal gas law. The kinetic energy can be separated into three different directions and add them together. Okay, it's a very useful concept. Okay, so and there's some example in textbook. I think they are pretty easy. Yeah, so I don't want to address them more. You can practice by yourself. Yeah, and this problem almost like the change of velocity equal to the work. Okay, you can calculate. Okay, so I just stop a video here. So anything else I have to address here? And no, okay, I just stop the video here and see you in next video. Okay, in next video we are going to talk about the power. Okay, see you. Bye bye.